All right, guys. So I'm recording. You guys are section one. Let's go there. Content. All right. So we essentially just have this week and next week, right, in terms of lectures to wrap up the semester. And then the following week is going to be project presentation. So you guys have your term project. And then after that, the final exam on finals week, that Thursday. So yeah, so that's kind of where we are today. We're gonna do something hopefully fun. We're gonna get into like the in-depth into deep learning, look at some gradients and like the calculus of it and everything. So it should be more of a, in-depth. It's still gonna be in PyTorch. We're gonna do a couple of examples of that, but to drive some of the ideas, we'll do that. And then likely in the last lecture, a week from today, we'll just cover a few last things like unsupervised learning techniques and some ideas of stable diffusion, the last algorithm of the course. All right, so that's kind of the semester for you guys. Okay. So yeah, so that's gonna be um I had planned to do kind of just give you an idea if you're still considering taking ITS 530, if you don't know. So that is, I think it's this one. So essentially, the key word here to understand what ITS 530 is the word transfer learning. All right, so transfer learning is the key term. So it's a course about transfer learning. So, and to put it in contrast with 520, you were doing everything from scratch, writing pure PyTorch and so on. So that's kind of at the lower level, right? So now you go to the other end, to the higher level, right? So that's going to be transfer learning, where essentially every problem, okay, let's find out if someone else has already trained a model for this, and that other can be Google or Meta, right? So that means they had massive amounts of data, massive amounts of compute, and so they were able to do something called a pre-trained model, a ResNet 50 for images, a Llama 3.2, etc. What's the advantage of that? Well, obviously, first of all, you guys know what it is like now to pre-train a large language model. That's not easy to do. You don't actually have the resources currently. But now you get to do that same problem, but this time you can start with at least GPT-2. And in fact, now you're only limited by the amount of compute that you have. I mean, if you had way more, you could DeepSeek, right? DeepSeek or something like that, and very powerful, Mistral, etc. So that, in this semester, I said you're not allowed to use libraries except PyTorch 530. You can use Hugging Face, transformers, right? Fast AI, essentially all those great libraries. And so that's the idea. So you can see here just to give you a taste for some of the things available. So there's going to be a lot of solutions for multiple problems. Fast AI, for instance, is going to be for your computer vision type of problem. And we can do things like image classification with fast AI. So you can see now the code becomes a lot simpler actually, because you'll be using libraries. So, you have your own special types of data loaders now. You're going to import from uh, over here. There should be Torch Vision. Oh, here it is. From FastAI import all, and that allows you now to bring in specialized models for your problems. Okay, so this is the data, for instance, an example of the data. Just processing with the data, playing with the data, some techniques. And then over here, you have these things called a CNN learner. So it's a type of so one of the key things that I'll say in 530 is that it's a lot of code wrapping, right? So what is code wrapping? Well, you guys were building neural networks this semester, but you would build classes, right? So it was always this class structure, init, forward, that's code wrapping, right? You simplify things because then you just use the model. So this is how these libraries work. They're still using PyTorch or TensorFlow underneath, but there's a lot of code wrapping to make your lives easier. So you can see, for instance, here you have a CNN learner, which you've learned about this, but notice the model that you're using is a ResNet 18. And in fact, it can be a pre-trained ResNet 18. What does that mean? It means that the weights are already learned. So that's a much smarter image or computer vision type of model. So it allows you it allows you to perform much better on your types of problems. So this is going to be one of the ideas. So essentially using pre-trained models, fine-tuning pre-trained models. So imagine your vet GPT or your GPT that you did this semester, but the data that you collected wouldn't be used for pre-training, instead for fine-tuning, which would be a second step after pre-training. So yeah, so that's one of the libraries, FastAI. There's of course specific libraries that we can use, which are not FastAI or transformers, but actually directly from the Torch hub, you can bring in pre-trained models for computer vision and so on. You can see that here this course kind of is ending towards CNN, and next week I'll do a very quick overview of the algorithms of stable diffusion, GANs, and then that we pick up in the next course, 5:30. But like I said, now from the point of view of transfer learning. So that is the emphasis. So solving problems with models. YOLO, this is for, maybe some of you have heard of this, for object recognition. So it's a very advanced set of algorithms for that specific task. TRL, it's a library from Hugging Face that we can use. So now new ideas will come in. It's not like we're just using libraries. New powerful ideas come into play now, such as reinforcement learning, right? So we're going to learn that we have pre-training, fine-tuning, and then something like reinforcement learning. So these are layers way after pre-training and fine-tuning. So that's the other component of training a large language model. So these are like the end stages now of training GPTs. Okay, so that's another one. So you can see here, reinforcement learning through human feedbacks is another big topic that we cover now. Some of the algorithms involved there. The advances with DeepSeek, for instance, they had some advancements in reinforcement learning, which were very elegant. Then Hugging Face transformers, of course, is a big component. Again, large language models, we're back to that. But this time around, from the point of view of Hugging Face transformers. So you can see over here, hello, I have a hello world GPT-2. And so in this example, I'm using the transformers library. So this is what we would cover. This is what I will cover anyway in 5:30 next semester. All right. So how to get, download a GPT-2, for instance, a pre-trained GPT, much larger, creating pipelines, etc., so that it can perform tasks. So you can see now these models actually already know language. And so what we have to do is improve them by doing fine-tuning, reinforcement learning, and those new ideas that are part of transfer learning. Okay. So that's kind of some of the topics. So go back. So, fine-tuning specifically, right? So, discussing how that works. A few advanced, like very advanced algorithms that we might discuss, including stable diffusion algorithms, the idea of weights as a transferable commodity. So you can now sell your weights, share your weights, right? This is really, really important. So that's one of the topics. And then some ideas in cloud computing, like using even APIs, right? So using APIs in the context of AI agents some tools like Replicate also, which allow you to deploy models to the web. Anyway, so that, just giving you a quick overview of some of the topics in the course in the course next semester, which is ITS 530, and it's, as I said, a course on transfer learning, the next course from this sequence. Okay? Any questions on that? All right, so yeah, so I wanted to give you that. All right, so now let's go back to this week's topic, which, like I said, should be a fun one. I really just wanted to kind of do something fun with this, and we're gonna look at calculus. All right, so but it should be very interesting, and I'll give you some examples of how the gradients work. We're gonna train a model, okay, almost from scratch. Like we're not even using, the optimizer per se. We're actually learning the weights independent. Okay, and so that's really what we're going to look at today. So the focus, we've completed here this module. We covered this last week, CNNs. By the way, before I forget, I did post the homework assignment for this one, so you can now have information on it. This assignment, as I said, is your last assignment, and I'm giving you until the last day of class before finals to submit it. Right, so that gives you plenty of time to complete this one. So we had discussed this assignment. Do you have a question? Pardon? The due time is you have until the 13th to submit. It'll stay open until the 13th, which I believe is the Friday, the last day of class. Okay? So yeah, so did you all have an event or something? You're all coming in late today. All right. Yeah, so that's the last homework assignment. And then you have your term project and you have the final exam. All right. So this homework assignment should be pretty easy, but here are the instructions. So using a data set of color images, train a CNN for classification and measure performance. The rules, as usual, you can only use PyTorch, train from scratch. You cannot use libraries to get the images. Like I did, you have to actually download a file, a folder with images in it. So you can get that from the internet. You must use actual images and load them into your environment. Remember, that's your challenge, right? So imagine in a company, they're going to give you a hard drive with images, right? You're not going to get a library that conveniently provides the images. Yes. Not necessarily. Oh yeah. Well, remember there's limits. So don't get 8K, 4K images. It should be 300 by 300, something like that, because remember, if it's 60,000 images, even if you're using Colab or something like that, it's going to be a lot. You see that? Yeah. So yeah, images take you to the limit, but that's the goal. Color images and so on, and then submit a report in PDF format with screenshots providing evidence of your work. Is this clear enough, or do you guys want me to add something else to this description? Clear enough? Yes, sir. Please. Oh, you can deploy it for bonus points, but I'm not gonna make it a requirement. It can totally be done, and I have it on my GitHub how to do it. You just have to find it. But essentially a website, a button, load the image. The image inside the JavaScript needs to be converted into a tensor, and then you send the tensor. So it's totally doable. Students have done it in the past. I think if you look at my ITS 365, you'll see examples there. But it's not required. Got it? All right. Yeah, so is this clear as far as the homework? It's not required though, but you still want it? Okay. All right. Can you send me an email so because I have to look for it. I don't remember where it is, but it's in my GitHub. Yeah. Send me an email and I will post it. Pardon? I will put it here and I will say bonus points deploy it. How about that? Yeah, it's something you might want to do for sure. Yeah. I mean, students in the past, they did one that ties it to the camera. So you can actually do JavaScript that ties to the camera, and then they did a sign language thing. So they would do like, you know how sign language, and then the classifier L or whatever sign language is. So you can do lots of things with it. All right. Yeah. So we talked about, like I said, ITS 530 and what that course entails. Keyword is transfer learning, as I said. Then we talked today about the homework assignment. So that has been given, and you have until the last day of class to submit that. Then, of course, you're all working on the term project, your NIO project. That's going to be the week before finals. Everyone needs to present their work and their groups in the final exam. So today, we're going to go, all semester, I've been trying to cover a lot of the topics that are very important. And this one is important, but it's more like, theoretical, although it's hands-on, but it's not something that you would do like if you were training your model, because you're just going to use the abstractions, like the code wrappers and everything like that. Here, we're really digging deep into some of the ideas. All right, but I think it's still pretty good to think about this. So we will cover hopefully these two modules today, and loss function. So this is just, I'll wrap up with these probably today. These are just like slides, which I kind of summarize everything, and then I have some code examples here for us to do. So we're going to train a model. I think it's I believe it's a temperature calculator, Celsius to Fahrenheit, but we're just going to code it up from scratch. Here, as usual, I provided some notes, so you can click on that, go through this material if you haven't done so already, and it gets into a lot of the details of this. Essentially, we're talking about optimization and gradients today. Okay, let's go to the table of contents. And I have a few examples that I will go through. So this is losses, batch normalization, differentiation, and gradients, and the code is provided here. Also, before I forget, I did want to cover some of the intuition of CNNs, and in particular, the convolution and how that works. So I have provided, we're going to go to the code. I'm going to start with that one. And you can see here, I have a Jupyter notebook on the math and convolutions idea. Right? So here we are. This is not how you would implement convolutions because it's not efficient. If this was the implementation underlying the convolution operation in our PyTorch, it would take forever to train, right? As you guys know. So these operations are usually converted to the equivalent matrix multiplication version so that it can be efficient, okay? But here, just for instructional purposes, I have provided this as for loops. So this one I'm not going to demo. I'm just going to go over it briefly to give you some ideas. So imagine, for instance, what is a convolution, right? So if you remember the CNNs, we talked about how we had an image, and then through that image, we would run a filter, right, over every pixel. And then for that specific pixel, we would look at the pixels around them, average them, and plug that in. So you can see that here. This is some kind of an image of a cup, okay? And then we're going to apply several filters to this image. And the point of that will be to take this image and transform it into another image, right? That's, if you remember, in the CNN, when we implemented, we had 16 possible filters. We didn't know what the weights of the filter were, but that's what the training learns. And then we know that the original image was converted into 16 different versions, right? So here is the intuition for that. As I said, this is the math and convolution operation. So here's the image. And here, if you notice, is a 3x3 filter. Do you guys see that? It's got positive values above, negative values below. This is called a horizontal edge filter. These are the kinds of filters that were developed by humans in the past. But now we know that machine learning models can learn these values and provide somewhat better filters. So what does this filter do? This horizontal edge is looking for exactly that, horizontal edges. Do you guys see that? And so now imagine here, this has been implemented, as you can see, in for loops. So this is the kind of thing that you can literally see it working, and it's something that you can understand, right? So imagine this image here, right? It's got indices i's and j's. So we can essentially then iterate with these two for loops over every single pixel in the image. And every time we are iterating over the image, notice what we're doing. We're processing it with the values in the filter. Do you guys see that? So here's the values in the filter, here's the value in the image, and we're processing all of them. And essentially what this is doing is it's transforming the image, okay? So that now look at what happened, what the filter did. Do you guys see that? It took the original image and it kind of grayed out everything that was not a horizontal edge, and the thing that is a horizontal edge has been highlighted. And do you guys see that here? This has been highlighted as a horizontal edge. Make sense? So that's the value of convolutions intuitively. You're transforming the images so that the neural network, what's it going to do? Well, it's going to focus on this. Hey, you know what? I'm finding horizontal edges in these images. And that's the information that might be relevant to me in my processing. Any questions on that, guys? So that's the idea. And so obviously, humans, as I said, spent a decade creating these filters, and this was very human driven. But then when you allow neural networks to do this on their own, you get move 37, right? They actually find out that actually that's not important, but this somehow is important, or some other calculation. Now here's an example of the vertical edge filter. So you can see this one is different from the other one. So this, look at how that one looks. This is how this looks. So there's courses called image processing, right? So you can, I took those courses many years ago, and I literally spent a whole semester learning all these filters, right? And it's funny. And, before CNNs were really, taking over. And so now we know that, we don't have to manually create these filters. Anyway, so the vertical edge filter, same idea, is applied to the image. And guess what? Notice how it highlighted in particular this area of the cup. Do you guys see that? So it's starting to find edges of the image, horizontal and vertical edges. So now maybe it's going to take, remember how neural networks go from one layer to the next layer, right? So here's an example visually. Okay, we applied one filter, it found vertical edges, or sorry, horizontal edges, and then it found vertical edges. And then what about a neuron that connects those two things? And now it's got edges both vertical and horizontal. And it starts to see, hey, you know what? There's a shape going on there. And so now I'm going to do a better classification of the problem. Okay, so that's the idea with and here's a horizontal edge with a stride of 2. So you can see it's a little bit more pixelated. So what is this representing? The fact that CNNs not only do the convolution, but also what is the term for the second step? The max pooling, right? And the max pooling compresses the data. Before, maybe it wasn't obvious that compressing the data was useful, but actually, look at it. Do we really need all these pixels to detect horizontal and vertical edges? This one still looks pretty good to me, and we have less information, still found, right, a horizontal edge, just with less resolution because it has been compressed, very much how max pooling would do. Do you guys see that? Does this make sense? Any questions? All right, here's another example, vertical edge filter with stride 2. And again, you can see there's the vertical edge, but it has been max spooled. So the image has lower resolution, but still quite informative. for the task. So that's essentially what CNNs are doing. Like if you literally wanted to see, this would be the example. Obviously, there will be, this is just a few filters, two filters really. There would be 16. Then we apply 32 to these images, right? And let's see now it's going to focus on these vertical and horizontal filters and to see whatever it finds interesting. Any questions on this idea? Now, the key thing, as I said, remember, it's not doing the 2 for loops. Nothing inside the GPU is 2 for loops, right? This operation has to be converted into the equivalent matrix multiplications to do this efficiently. And that's the heavy lifting that is done by conv2d in PyTorch. All right. No questions? Yeah, good. Sure. That's the idea. Like that's the standard approach with CNNs to do the convolution followed by a max pool. And the max pool is doing this, like I said, as you can see here, here's full resolution with stride 2, which is equivalent to max pool, obviously less resolution. But yeah, I mean, you do have full resolution in the first layer. So you haven't lost it there, and you're applying 16 filters or 32 that the model, we don't pick them, right? The model will try 32 filters, performance is bad, so it's going to keep training until it finds the right set that produces the highest results, because that's what stochastic gradient descent is doing. Yeah, you're right. It's doing it by itself. So remember that these filters, we don't hard code, right? This is equivalent to the weight matrix before. It's literally that. And so we just initialize them randomly, and we say the specific size and the number of filters, but the model is trying different ones, not randomly, but through stochastic gradient descent, which means it optimizes to the. That's right. Back propagation is happening. So you put in, let's say you're doing animals, right? So, breeds of dogs, right? So German Shepherd, other dogs, right? So Doberman, so the image comes in, it goes through the network, right? Filter convolutions, all of this to produce the final result, which is actually just a class. Which breed is it? German Shepherd. You compare to the real, it made a bad prediction, so you back propagate that error to update the weights of the filters. For images? Yeah, so in 2012, the 2012 competition, they had 1.4 million, and that was considered a lot back then. Today, with the computing power they have and everything, is think about Google and Meta, how many images they have. Got it? Make sense? Yeah. So, oh yeah, please go ahead. The filter size, that's just, you have one pixel, and then that pixel looks at all the pixels around it. So the way to understand it is, this is the pixel you are at on the image. Do you see that? You can make it 5 by 5, but you don't want it to be too big. This is like paying attention to just the local pixels around it. So that's a good question, actually, because CNNs are like this idea that you don't actually need to pay attention to everything. You just pay attention to a patch or a local area of the image. So this essentially just means it's paying attention to only the pixels around it. And then it's gonna, look at the values here in the image and multiply them times these values in the filter, and then add all of that to assign a value here. Do you see that? Yeah. So that's, the simplest case of applying a filter. And you essentially do that operation, and the image is now being transformed from the original one, which is this cup, right? And has a lot of details and everything if you look, to just this, where the only detail really is this one. There's a little bit going on here too, because that's also correct, right? This is a horizontal edge. Got it? Yeah. So yeah, so intuitively, this is the convolution operation. You can run the code, it'll work, and just to get a feel for how it is and visualize the image. All right, so yeah, so like I said, I'm just going in depth on ideas today. So the next thing that we're going to look at is we're done with CNNs at this point. Okay, so hopefully that, we covered a little bit of the theory and how to implement the code. Now we're going to go into this one, losses, batch norm, differentiation, and gradients. And we really just want to understand what is happening behind the scenes. Okay, so I'm going to click on code, and this is going to take us to a few scripts. And we don't even need data sets for this one. We're just going to, bring in our own. So I'm going to use Colab for this example to illustrate. Colab. New notebook. Okay, let's add a few cells. All right. So here's a few examples that I have. I have an example on just normalizing a batch, for instance. I'm going to leave that for later. I have this one, scratch gradients, losses. We'll cover that one. And I think this one is where I'm going to start, just to motivate everything. Yeah, so this is essentially, we're going to train something from like scratch, like literally from scratch, without using Optim, without abstracting anything. We'll use the gradient mechanism, autograd, just to see what it is. And then we'll drill down even to some of the calculus approaches. All right, so for this example, let's title this one Scratch Optimization Learning, or we can also call it Basics of Optimization. I'm going to go back to the simplest case, and I'm just going to use a linear function just to keep it super simple. But you guys already know how this works. So we have x times w, which is the weights, plus b equal y, correct? Or this could be equal to h1, and becomes hidden layer, and that becomes input to the next layer. And I will summarize this today with some slides. So we're going to have some data, and the data in question is the conversion from the units of Celsius to the units of Fahrenheit. Okay, pretty simple neural network, but you guys know, and this actually brings in something very interesting, like a thought, right? There's an equation, correct, to convert Celsius to Fahrenheit. We all probably learned it at some point in school, elementary school, perhaps. And you know that there are equations that govern the laws of physics, right, guys? There's equations, right? And, usually those equations are associated with geniuses, right? In history of humanity, right? So E equals mc squared, Albert Einstein, right? And he came up with that idea. But as it turns out, machine learning, just by looking at data, can do the exact same thing, because these functions are universal function approximators, which essentially, like in this case, there is in fact an equation from Fahrenheit to Celsius, right? We don't have to train a model, but a model could look at data and approximate through a neural network so that when you give it an input, it predicts correctly. So the same as an equation. So my point is, as humans, currently AI is at its early stages. Only the application has been mostly to images first, then language. It's only barely starting to get into like industrial processes, like what you guys are doing with NIO. let alone looking at physics, and things like that, chemistry. Think about when AI is like very robust in that domain, like it is in image processing today. And it starts to discover new equations and new things, we potentially will have new physics, new chemistry, right? So because it can do this, where a human, it takes it a year to do just one, it can do thousands in a year, right? So anyway, so that's a very interesting idea. Kepler did the establishment of equations for the movement of planets and things like that, thanks to some data collected by other famous astronomers in history. And then he came up with some equations, and that today you give it to a machine learning model, it'll figure that out as well. All right, so there is that power. So I like doing this example with because it's an actual equation. Today we can learn the Lorentz equations, which is a system of equations, and you can teach it to model, the atmosphere. Just again, this is called, by the way, data-driven engineering science. And so the idea is that you can do all that stuff that they've been doing in the sciences, but it's data-driven. As long as you can get some data, maybe you have the laws of physics, you simulate that process, and as you're simulating, you're collecting data over time, and then that data can be given to a machine learning model, and then boom, you have an entirely new apparatus. All right, so let's go ahead and get started with this one. So I motivated a little bit. So now, as you can see, we're going to do everything from scratch today. So we're going to use Torch, Matplotlib, NumPy, the libraries that should be pretty familiar to you at this point. So that's done. Now we're obviously data-driven means this, right? So if we were doing, if you remember your science courses, etc., when you were taught about temperature and things like that, you were not given data. What were you given? Some equation, right? Everything was an equation. Here, when you take this from the perspective of AI machine learning, it's data, right? So what do we have here? We have the data. So you guys help me out. So which one of these is Fahrenheit? Let's change because I'm going to get confused here. This is Fahrenheit, correct? So 35.7 is equivalent to about 0 degrees Celsius. What's the highest here? 68 probably, and seems to be about 21 Celsius, right? So essentially that's the idea. We can try this out later. So we don't have the temperature of, say, 100 Celsius, which should be what in Fahrenheit? 212, something like that. Right? So we'll test this out if our model worked correctly. But now we have our data. I'm going to proceed. Okay, so I've collected that. So let's just print out the data. We're going to convert it into torch tensors. So I'm using TU is going to be TF. I don't know why I was using U before. Yeah, remember? But anyway, TF, so Fahrenheit, both are torch tensors now. We can print out, oh yeah, I didn't. We can see we got our data there. These are now torch tensors, okay? And we just want to train a model that can predict this model, a linear equation should be enough. So we don't really, and it's a regression problem, right? You guys have been asking that question a lot, so you should know exactly that this is a regression problem. Okay. So now let's go ahead and plot it just so that we can visualize it. So it's a plot of Fahrenheit to Celsius. Let's change this one to be TF. We're going to change it to NumPy. And we should be able to see it. So as it gets to 80, it's around 25, it seems, 20, 27 possibly. Definitely 0 is about here, and that is what in Fahrenheit? Seems to be about 32, somewhere like that. Do you guys agree? Any questions? All right, so we plotted our data. We have this available. Now let's proceed to create a model. We're going to create a simple model to be a little, I'm not going to create a class for this one, but I'm just going to use the actual equations. So this will take TF. So it seems that we're converting from Fahrenheit to Celsius, right? So that's the plan. W and B are what? They're going to be the weights and the biases. So we know, in fact, that the equation that we're creating is y equal W times X plus B, right? And the parameters are W and B. This is not a mystery. We've been doing this all semester. Should be familiar to you. I'm going to change this to TF here. So I'm going to take whatever my F value is times the weight matrix, which in this case is a vector of 1 plus the bias, and that should give me my Celsius. Make sense? So we have a standard layer of a neural network, the linear layer, that we can try out. Okay. Now, here we're going to do the loss function. So we've thoroughly gone over cross entropy, right? So we went over cross entropy in great detail in one lecture. Today, we're looking at MSE, of course, the mean squared error. So I'm not going to use the PyTorch function, but instead we're hard coding it. So this is going to be the loss Fn that takes the real and the predicted. So it's going to be y minus real squared. Do you guys see that? Okay. Any questions on that? And so that's going to take essentially the values, right? And then we just take the mean of that, assuming we have essentially a batch of values, something like that. Okay. But we take the differences between real and predicted and we square them. Got it? All right. So let's go ahead and do this. Okay. So now we're going to define our training loop as before, but this training loop will be a little bit different because we're going to be hard coding certain things. Okay, so let's take a look at it, or we're going to be replacing certain things with, more low-level approaches. So the training loop will take the n epochs, it'll take the learning rate. What was the learning rate? We were adding or subtracting something from the weights, and that something is the learning rate, the little step. Okay, so learning rate, we have params here, and params is going to be, for this example, the number of weights and biases. So we have one weight and one bias. In DeepSeek, you have 671 billion of those, right? Params. We've done other models where we had 12, I think, or 14. And so it can get really large. But that's the weights and the biases of the neural network. This is going to be TF. That's going to be TC. Okay. All right. So we come in for epoch in range from n to epochs. So we're going to train our model. None of this is a mystery. Right. Here we're going to look at zeroing out the grad. Okay. Okay. So this is just essentially params.grad is not none. So we are going to zero out the grads. This is just the same thing as before where we've always zero out the grads. Okay. Now the model here takes in, you have the model, so it takes in TF, the Fahrenheit. And notice here something interesting. We are passing as a pointer the params. Okay. Do you guys see that? This is different. When we use NN linear internally, the weights and the biases are created, right? And so we don't have to handle it manually. But here, to illustrate this further, the parameters W and B, these values here, W and B, are going to be separate. Okay, they're a separate thing. Imagine that's the thing that we want to train, right? And there's only two values in there. We're passing it as a pointer because essentially there's two. So that way we just point to the space and memory where they are and we can just retrieve it. That's just a mechanical thing. So essentially this function takes in TF and it takes in params. So if we look at the function, yeah, here it is. It takes TF followed by these two values. We're providing a pointer to params which contains the two values. Okay? Got it? And those two values are separate today just so that we can get a better understanding of what's working. Well, we're also going to randomly or initialize them to 0 or something like that, just so that we can see the trait. Any question on this, guys? All right, great. Sounds good. All right, so we have TF and params. That, when TF goes in, it provides Y pred, so that's going to be your temperature in Celsius. Okay? So, and then once we have our temperature in Celsius, we're going to take the loss function. So the loss function will take the difference between TC, the real value in Celsius, and the predicted value in Celsius. So obviously, initially, these are going to be bad predictions, but we're minimizing this error. So the weights are going to be updated so that eventually it makes good predictions. Got it? Yeah, and this is the mechanism. Now this step happens here, loss backward. What would happen in loss backward if you guys remember? We would estimate the gradients, which essentially is we would take the derivative of the function, right, in terms of some value, and that's when we would know the direction. Are we adding or subtracting, essentially? Got it? And we will see this actually in the next example. We'll start playing with those ideas a little bit more of what's happening. But just for now, remember that this loss backward does the calculus part. Okay? And so later I'm going to keep using loss backward just so that we can see the values before the calculus part and after. All right, so here we've taken the values. So I know when I did this that params has now been calculated. Do you see that, those values? Okay, so now what do? I'm going to notice here, with torch no grad, right? I'm going to, let me do it this way, params minus learning rate. This is called the update rule. This is something that you guys have not seen all semester because we do op.step instead, right? So, and that's what PyTorch is doing for you, but essentially what's happening inside is this, the update rule. So if you look, params equal params, right? The W and the B, right? So we take those values, we do minus, right? But this is the important term. We have two values here, learning rate, which is a value such as 0.003. Remember? So that's like a step size. That value does not change. It's the amount by which you're going to update the params. 0.003. If you use 0.05, it's a bigger update, which may not be a great idea. If it's 0.00003, it'll take forever to converge. And then here is params.grad. So this is what the value of the derivative is at that point. So every time you're taking that derivative kind of to know which direction to go, if you guys remember. So this is more important in terms of direction than it is in terms of value. So if it's positive, then positive learning rate minus, what do? You decrease, right? The size of params, right? For each one, because they're individual. And if it's negative, what happens? Negative becomes positive. So we add this learning rate to the params. And that's it. This is the magic of updating the weights. There's no real mystery to it. So this part is easy. And then in another Jupyter, we'll explore this in a little bit more detail, but that's the idea. Keep in mind, params here is two values, right? And that's the secret. So you have two params. This is a model of two params. And so we need two values here. Imagine if we were doing DeepSeek, 671 billion parameters, right? So it's almost like we'd have to do for all of those, this procedure. Got it? Any questions? All right, so that's it. That's the code for this one. And then we just print the loss value, right? This loss every 500 iterations or so. That represents the error, and this error should be going down. At the end of training, what's the thing of value that we want, really? What's the model? Params, right? We know the structure of the equation. It is just what? Y equal W times X plus B. So that's the structure. The X's we had. So really the value that we need is W and B. So one AI person, a famous person said, when people were really scared of AI, right, that it's going to take over the world or something or kill us all, you know what you're really afraid of. You're afraid of a table full of weights. So essentially, if there's something to be afraid of in terms of AI, is params. Params is the boogeyman, right? So that's it, because that's where the intelligence is. We know the architecture, like in a GPT, but we don't know the values of the weights. That's the thing that we have to get. This is a good segue to say in ITS 530 transfer learning, what we would want to do is I want you, right, to train the model. When you're done, can you please email this to me? And then I just take that, plug it into my thing. Guess what? That's transfer learning. You guys see that? So that's essentially the entire idea. We rely on Google you can do this one, but if I ask you to do a GPT, right, with all the data in the world, you can't do it. So, but Google can, or Meta can, DeepSeek, Mistral, whomever, and then they provide that as these weights. And then you just load them in your architecture. So that's why nowadays people are writing their own transformer or their own GPTs in C++ or whatever for robots, and they can still load these weights on there because they're just values. Do you guys see that? So that's essentially the idea. All right, so let's instantiate this training loop. Okay, so that's done here. Yes, please, go ahead. Sure. That's the scheduler, right? Do you remember last class where I introduced the scheduler? Yeah, so you could also manually write an equation that decreases it. So by every iteration, the idea is that it would get smaller over time. So you could do that manually. The scheduler is smarter at doing that. Yeah, totally doable. All right, so we have our function over here. So that's done. Okay. So hopefully that made sense because you guys are literally doing this from scratch at this point. You would not be able to do the differentiation because that's doing calculus, right? So that has to be there. We need a solver for that. There's a chain, something called the chain rule. And that's really what PyTorch does. And amazingly, this one line of code does all of that for us. So think about how that was simplified to just one line of code for us, which is massive underneath. Okay. And we'll explore that a little bit later. All right. So now that this is done, we're just going to go ahead and call the training loop. So I'm going to go over here. So here is my function, training loop. I'm going to train for 100,000 iterations. I'm going to give it a learning rate of 0.001. And notice this is really important. But because you guys are, you've already understood NIO, you can see that this one is pretty much like NIO, except not for the input, but for the weights themselves. Notice that the key because you're creating a computational graph, the key in everything is to provide this parameter. Requires grad equal true. So when you create a tensor, a torch tensor, you indicate whether it requires grad or not. Weights and biases obviously need to be updated in the computational graph, and therefore they requires grad. What do we initialize them to? Just 1 and 0. This is not even a great initialization, but it's initialized to something. All right. Any questions on that? So this is really important as these are the parameters, but remember these are external, not tied to the equation itself. Okay? Then TU is TF, both internally and externally, and TC is the Celsius. So now we can go ahead and run it, and remember, result will be the params. So, what's the error? All right, why is this giving me an error? Calculated one loss, right? Calculated this loss. Here, it took the difference, so the loss backward. Backward. All right, so it's 6:04. Let's do something. Let's take a 10-minute break here. Let me debug this. And let's come back at 6:14 and hopefully I'll figure it out by then. So just, yeah, it's 6:04. Let's take a 10-minute break until 6:14.